have two talks today. The first talk will be from Benjamin Turnbull, and it will be about Conway's Game of Life. Give him a warm welcome.
Okay, hi everyone. So the title of my talk is John Conway's Game of Life, a Cellular Automaton Safari. So this is a mathematical game that was invented in 1970 by John Conway, and it's got a lot of analogies to life. There's a lot of interesting so-called life forms that you can find with it, which is why we've got the title there, because it's not going to be that technical. I'm mostly just giving a tour of everything and showing you what it does. So to start with, I need to tell you what a cellular automaton is, even if a lot of you might already know. And I actually want to start with a bit of a simpler example than Conway's Game of Life, which is one that was invented later in the mid-'80s called Langton's Ant. So Langton's Ant is actually a lot more similar to a standard Turing machine than a lot of other cellular automatons. So a Turing machine would be where you've got a machine that has a finite set of states, and it can write on an infinite tape of some sort, and depending on what symbol it sees on the tape and what state it's in, that determines what it writes. Langton's Ant is a very simple one, where you start with one spot marked on the tape, and the rule is it starts going in the vertical direction. Then if there's a white spot there, it changes the color to black, then it turns right, and then it moves to the next one, and so on like that. So we can sort of step through what it's doing. Now once it gets to a black square, it's going to flip the color, but this time it's going to turn the other way. So you see now it's turning right again because those are all white squares, but then it has to go backwards. And it just evolves like that. And to start with, the pattern is sort of fairly simple and geometric, and it kind of looks like it's going to keep repeating itself. But it very quickly becomes a bit more chaotic if we'll just let it go a bit faster. So, as you can see, very simple rules, but there's no information to start with. You just start with others because there's only one cell that's really active. You can sort of see the ant itself moving all the way around. Conway's Game of Life is a bit different. In Conway's Game of Life, every cell on the board is active. Now, I'm just going to fiddle around with the controls a bit here because I don't know how to get this to work any other way. Go white again. Yeah, so I'm fiddling around with the software program to change the rules to the Game of Life rules. So what are the Game of Life rules? Well, now all of the cells are active, but the idea behind the Game of Life is that some of the cells are alive, those are the white ones, and some of them are dead. This cellular automaton was invented to try to sort of mimic in some ways the way populations of cells might grow and change. So you have rules that tell you when cells are born and when they die. So one of the rules is that cells can't just be born out in the middle of nowhere. They have to be born attached to others. And the rule that was chosen was you specifically have to have 3 neighbors. And neighbors are neighbors that are going to be diagonally or across from each other. So, for example, with this group of 3 cells here, these neighbors on either side there's exactly 3 neighbors, so a cell could be born there in one step. And like if you do step it, this will step all of them, but you will see that those ones go there. And a lot of cells also disappeared because there's death rules as well. So if there's a cell that only has one neighbor, doesn't have any neighbors at all, like these two, then those are going to disappear. And then the last rule is just the survival rule, which is, and then there's more death rules for when cells are surrounded by too many neighbors. So if you keep an eye on this one here, this one's got 4 neighbors. Anything that's got 4 neighbors or more is going to disappear. So in one generation, that one's gone. But you see one above it just got created because it had 3 neighbors. So that's basically what it is. The rules are you get a cell is born if it has 3 live neighbors, and it survives it has 2 or 3 neighbors. Everything else is going to die. And these were chosen more or less completely arbitrarily by John Conway because he just played around with the numbers till he found something that looked interesting. Which is different from the very first cellular automaton, which was proposed by John von Neumann. He was actually trying to create something that would mimic that you could construct machines out of that would mimic life in some ways and would actually be able to reproduce itself. So instead, what's interesting about this one is the approach is completely from the other end. It's just trying to set up the rules for something that looks interesting and then looking at what happens. So that's mostly what we're going to start with, is looking at what happens, which is why here I've got this set of sort of n dominoes. We've got a domino here, these 2 are triominoes. The ones there are your standard tetranomos, and then the rest are pentominoes. So we'll just sort of go through the generations. You can pick ones that you want to. Like if you look at the square and the one with 3 above it, in one generation the one with 3 becomes a square, but the square stays the same. Just stays that way the whole time. And now if you look at the 2, there's 2 of them that have a group of 6, and in one generation those become these sort of round shapes here that are called in the Game of Life lexicon beehives, and as you keep going those stay the same. That one that we saw at the beginning, that triangle there, is just oscillating, and we notice that there's a bunch of others that are oscillating as well. So they're all sort of fairly simple and basic. These ones are often called beehives, these ones are called loaves, these ones here are called blinkers. It's actually very common to get, as you can see, a pattern where you get 4 of these blinkers at once, which is why they sometimes call those traffic lights. And that's what this is going to be about. We're going to just talk about these patterns and what they are. So there's 2 types here. We've got 2 types of patterns. These ones that oscillate are sort of period 2 oscillators, and the rest are just what are called still lifes. So I picked these because I actually like to play, I don't know if any of you play this game called Blockus, but that uses pieces that are exactly like this. But that's also the way John Conway started experimenting with the Game of Life, is he used all of these sort of n omnis up to 7. And if you are familiar with Blockus or just familiar with all of the shapes, you might notice that I left one out here, which is a major oversight. So what I'm going to do is I'm actually just going to quickly make a new file, and I'm going to draw it here. Yes. This is the one I left out, and it's a little bit weird. So we're just going to start stepping through it. And we see it's definitely not settling down like the others. And we can actually keep going, and it's just going to keep going like that for a while. Now, it actually does eventually settle down, but you might have noticed that there's some little patterns that are running away from it. We'll get back to those later, but what this basically is telling us is that it's not really that obvious just from the basic shapes which patterns are going to settle down and which ones aren't. It's because this is basically like a Turing machine running in parallel, it's very similar to the halting problem. You don't really know on a given configuration how long something is going to keep changing, whether it's going to come to a stable configuration or not. So that's the first question that we sort of run into. That pentomino that we started with is known as a Methuselah pattern. which is a name that's given for any pattern that's sort of quite small but develops to a much larger pattern when you let it go. Another example that we can look at is the acorn. And I'm just going to zoom out a little bit and we'll just run that one. The acorn's just about the same size, but it actually runs for even longer, so we'll just sort of speed it up a bit and maybe go out one more step. So this pattern here, you see a few more different shapes there. We've got our usual sort of these blocks here. We've got these blinkers. We've got beehives. These things are often called boats. And there's this round one is called a pond, and this one is called a mango. So it's the people who play around with this have a lot of fun with these. But you sort of start to wonder, well, if you can get growth like that, is infinite growth possible? Also, the patterns tend to sort of settle down to a few of them commonly. What are the most common patterns? And also you can try to think about working backwards. And some of the first things that were proved with the game of life had to do with working backwards. And it was finding patterns like this one. I'm not going to actually evolve this one because it's not really that interesting. As you can see, there's going to be a lot of dead cells because it's way too dense. But this pattern was the first one that was proved to have no parent. Because since the rules aren't symmetric in the game of life, they're not reversible. And the question was just, well, is there a pattern without a parent? The answer was proved 1 year after John Conway proposed the question, and this was the answer. Later, a whole bunch of other patterns were found that were similar. But there's still innovations going on with this right now with people who are doing this sort of mathematics just for fun. And just in 2016, the grandfather problem was solved. And this pattern was discovered. This one does have a parent. It actually has a lot of different parents that will all evolve to this state, but it doesn't have a grandparent. And so similarly, I think this one was solved, and then also like great-grandparents and others. But there are still some open questions, like I believe the finding a pattern that has a unique parent, the unique parent problem hasn't been solved. So finding a pattern that does have a parent, but proving that parent's unique. So lots of work still out there. And so you can go and play around and sort of just scribble around and make your own patterns. And one thing that people did was they decided to just systematically try integers. I don't know if you can actually read these, but all of these are just sort of integers done in block letters. Now obviously we don't have all the integers here. We've just got the ones that happen to be interesting ones. So they've got the patterns beside them of what they actually evolve into. And then if you run them, that just demonstrates that those integers actually happen to go into those. So these are a lot of the sort of ones that come up fairly frequently. A lot of these ones here are a lot more rare, especially these larger ones. And we've got some oscillators that are a lot more interesting there. So actually I put down the top 20 or so of this is the top 20. Someone actually did a census of just drawing random dots and letting it evolve till things stopped happening. And these are both the top 20 still life and oscillating patterns. So we've got like the loaf boat, that's called a tub pond. They often call these ones ships, and those are that's like a longer boat. This is a beacon, and that big fancy one is called a pulsar, and even though it's quite large, it happens to have a fairly simple starting pattern that evolves into it, and just why it actually often shows up. Not particularly often, but you can sometimes find it. So, oops. that was me getting ahead of myself. We've got more sort of common still lifes here. If you evolve these ones, nothing happens. And there are some low period oscillators. So they've actually sort of they've drawn in the number. You've got period 2, 3, 4, all up until once you get to 16, then it's sometimes a bit harder. It's actually somewhat easier to find larger period ones, depending on what you do. But maybe we want to get back to some of the, these patterns are interesting, but we want to get back to those things that we saw flying off before. So, So beforehand, when we did we did those Methuselahs, we did the acorn, and we did that sort of pentomino that did that there, we found this pattern. This is called a glider, and this one is also one of the patterns that shows up a lot. And because this one shows up a lot, this is what makes life particularly interesting. After 4 generations, 1, 2, 3, 4, this pattern is exactly the same as it started, but it's moved diagonally. And it just keeps doing that. And this one is called a glider because it moves. And in general, any pattern that moves like that is called a spaceship. So there are other patterns like that. We've got these ones which are called orthogonal spaceships because they all move, rather than moving diagonally, they move orthogonal. So these are the simplest ones here on the left. If we go through those, in 2 steps they've moved and now they're mirror images. And then in 4 steps they've moved 2 and now they're mirror images. That's actually the fastest that a pattern like that can move. These ones are not all actually moving at the same speed, so some of them are sort of slower. And what they often call that is they sort of describe the speed of these things as some fraction of c. So c is the speed of light in the game of life, and what that actually refers to is basically moving one cell at a time. So, for example, if you do a simple pattern like that, you can see this one is going to move one cell at a time. That's the fastest that it can move. It turns out for a spaceship, the fastest it can move is actually c over 2, because it has to change shape as it's going. So it can't actually move itself an entire unit unless you've got some sort of medium for it to move over. So besides the glider, there's also other diagonal ships as well. Some of them involve gliders. You can actually see this one's got a whole bunch of them there. And an interesting fact is that these two are actually referred to, I think this one, I'm not sure about the other one, I think this one's called the Canada Goose. The other one might be called the Swan, I'm not sure which is which. But, yeah, interesting facts right there. So, another thing, these simplest ones are called the lightweight spaceship, middleweight spaceship, and heavyweight spaceship. And you sort of see how one's just getting longer than the other, and you might wonder, why can't you have one longer? And the reason is that this spark at the top, or this little thing at the top, once it gets too long, it starts to interfere with itself, which is why we've got a longer one down here. And this longer one is okay because it's got a couple of smaller spaceships beside it so that it can move. But if you decided to get rid of one of them, then you'd see that very quickly it would start to destroy itself. So that's sort of getting into the start of some of the engineering that people have been doing with the game of life. These patterns are fairly simple and you can discover them on your own by just trying things randomly enough. But once you've got a few patterns, you can kind of add them together and try to make interesting things happen. So one person who started doing that early on was someone called Bill Gosper, and they discovered a pattern, this one up here, which is something that just naturally occurs. So this is sort of an oscillator, and the way this one was discovered was actually by just looking at things randomly happening. So one way you can get a pattern similar to this, whoops, I'm on the wrong thing, is to use one of the hepdominoes, domino with 7 pieces, called the pi hepdomino. If you go through a few generations of that, you see it sort of making these triangular things that are similar to what's going on in that oscillator. And that's one that actually shows up quite frequently. Yeah, you'll have to bear with me on this. This is not very well practiced. So actually, if you don't have these blocks in just the right place, if you watch what this does, is it creates one of these beehives there, then it creates another one on the other side that heads back in the same direction. That's why this pattern is actually called a queen bee. Now, if you let it keep going from there, it just kind of destroys itself and ends up with this little uninteresting pattern here. But once you put the stabilizers in, you get this interesting thing. And you can see that there's sort of interesting interactions that are happening on either side. Well, what Bill Gosper did is decided to get 2 of these together and sort of look at how the collisions between the 2 interact. So now there's 2 of these queen bee oscillators, but only 2 stabilizing blocks. So they end up colliding in the middle. And I should probably scroll down a bit here. And what happens when we run this one is once they collide, they actually produce a bunch of junk that eventually turns into one of these gliders. And that keeps repeating itself. So this was the first discovered linearly increasing pattern, and that's basically the proof that yes, from the starting condition, you can increase indefinitely. Interestingly enough, like that pattern itself, you have to have these 2 queen bees that are carefully aligned. It doesn't happen that much naturally if you just draw some random chunk. But after this one was discovered, another one was discovered that actually, getting ahead of myself, that actually does happen randomly. And that's because it's such a simple pattern. In fact, this here is the whole pattern. This block here is just in there to stop it from destroying itself before it starts to grow. So with this one, this one moves a lot more slowly. But you see it's a very complicated reaction, and it starts building these blocks, but then it keeps going. It reminds me a little bit about Langton's ant in that highway, especially since this happens more often naturally, so the pattern is a bit more of an attractor than the other one. That one is called a quarter ship, often after Quarterman's the guy who discovered it, or sometimes it's called a switch engine. And from there, one of the natural questions is, okay, well, we can do linearly increasing patterns. What about a quadratically increasing pattern? So, or like, what about other like linearly increasing patterns? And there's another type that's sort of similar to that was discovered. This is one of a pattern that shows up a lot that's unstable. But again, we've got these 2 lightweight spaceships here that help stabilize it. And this one's sometimes called a puffer train. This one kind of creates a lot of junk behind it. And you end up seeing a lot of these patterns, but again, it's a repeating pattern because it just keeps going on like that forever. But yeah, as I was saying before, like that example, the next question that Bill Gosper was dealing with was, well, can you get quadratic patterns? And so basically what he managed to do was find a way to create spaceships that would emit gliders and then aim the gliders in such a way that their collisions would produce more of those Gosper guns. The Queen Bee collision thing is called a Gosper gun after Bill Gosper. So in this case, that's basically what happens. You can't really see the whole thing there, but all of the blocks that are being produced by different puffer-trained spaceships that leave certain types of junk, some of them emit those gliders, and then at the end you get all of these things working together. So this is quadratic growth, and that's the fastest kind of growth you can get because we're only in 2 dimensions here. You can only move at a linear speed. Still, that was improved on as well with these space fillers, which are a lot of fun to watch. So in this case, this one is called Max because it's the smallest pattern that was found that can create a space filler like that, and this is the densest possible pattern you can have, because if you were to try to add extra dots in somewhere, it would all completely fall apart. And this is a lot of fun to watch, although it'll start to task the processor a little bit after a while. This program actually has a lot of tricks to compute generations really fast, provided there's patterns. When something like this happens, it gets a little more tricky. It has to do everything. Parallelization helps. And there's something interesting. There's one of those pulsars. So, see, they can sort of happen in random junk like that. So, don't save that. So, that deals with basic growth patterns and like that. You can also look at more complex growth patterns, and since the people working on this are mainly mathematicians, one of the things that was designed was this complicated piece of machinery. So this was designed by Dean Hickerson in 1991, and this is a prime number generating sieve, basically. So what happens is we're producing these spaceships here that are going out, and the idea is to delete any of them that aren't a prime number. So we've got 2 and 3 there, and then we get 5, and then we get 7, and it's basically keeps going. The way it works is that it's creating these gliders that are bouncing back and forth, and these ones are basically deleting all of these by colliding with them. We'll have to sort of wait to see when it actually happened. This one's probably no. Well, so some of them get collided with, and then as you go, it creates more of these glider paths. It basically works the same way as typical prime number sieve. You're just sort of deleting them all. This pattern here helps delete the. I think that one sort of does every 15, so it helps deal with the 3s and 5s. But yeah. So with a lot of those patterns, there's a lot of clearly some kind of engineering going on there. And that's one approach that people often make with this, but there are other approaches to make as well. You can also make computer programs that are going to just search the space for interesting patterns that oscillate, that are periodic, or they're quasi-periodic, meaning they're like a spaceship where they slightly move. And one of the interesting things that was created that way were all of these patterns. And this is where the game of life really starts to look a bit organic, because like a lot of these were discovered sort of by getting something that almost worked and then sort of gradually tweaking it using a I think they used a genetic algorithm of some sort. But these things are all patterns that move, and they move in a very sort of organic way, like little critters. So even these ones here are moving. It's just kind of slow. You sort of speed it up, and you can get a better idea. And there they all go. So quite interesting things can go on with this stuff. So, oh yeah, this one's actually sort of out of order. This is another engineered example that was made specifically for this program, which is called Golly. So here, they've got a lot of gliders that are sort of bouncing in between there, and all of these things are basically guns that produce spaceships rather than gliders. But what's happening here is that those patterns that the gliders are in are actually very specific because they've actually encoded a series of bits so that they can make a ticker tape like that. It would have really impressed you, I'm sure, if I could have arranged them to actually sort of spell my own name or something like that. But I put this kind of together at the last minute, so I'm just using their example. So, and again, like with a lot of these constructions, they're looking at ways that you can make these. So it's not only about just building these things statically, but also thinking, okay, what's the simplest way I can generate one of these things? Or maybe, like, how can I build up this complex stuff by just firing gliders around? So, like, maybe if we just go back to this example here, this one, remember, mainly worked by just having gliders running into things and gradually changing them. So since it's a common pattern, it's easy to produce, a lot of what you try to do is based on just looking at how those things work. So these are all of the different ways that two of these gliders can combine. If you have three or more at once, you can get even more interesting things happening. So a lot of them, when they hit, nothing will happen. Some of them will turn into those blinkers. Some of them will turn into another glider that will be deflected. And then there's more that are just those still life ones. And you can see the one at the bottom is just sort of called a two-glider mess because it just kind of messes around into a whole bunch of stuff. So all of those basic shapes are things that you can make if you just have these glider guns that are aiming specifically at them. And based on that, this much bigger pattern was constructed. And the idea of this is to make some kind of a general constructor. So there's a lot of things going on. First, this line here is just a line of gliders. In a sense, it's just a string of data. And this square thing here is a loop that reflects the gliders around and also duplicates them. So it's just kind of like a memory storage. And then all the other machinery deals with what this thing actually does. Let me just... So we'll just run it and speed it up a bit. There we go. Okay, there we go. So it's kind of hard to see what's going on. We're firing gliders here, and then there's a block that's sort of moving in a jerky way. But if you slow it down, what's actually happening is they're using glider collision. This is actually a printer. It's using glider collisions to move this block, which is like the print head. And then some of them are fired at an angle so that they go off. And then it just hits this debris, and it constructs a line of these hooks. And so that long line of gliders at the beginning was actually a program that gets stored in here and repeated. And that program basically tells it what sequence of gliders to fire in order to keep printing that sequence. So this is actually one step away from one of the things that people have been trying to do for a long time in the game of life, which is to make a replicator, make something that can make an exact copy of itself somewhere else while still existing. So this is kind of like a printer. In order to actually make a replicator this way, you'd have to make a printer that's able to print itself. And so far, well, it's been proved for a long time that that's possible, and someone's even demonstrated a way that using instructions like this, they could do it, but the thing would actually have to be huge. So I'm getting sort of near the end now. I wanted to spend a little more time on these really huge patterns, but there's not really going to be a lot. So this one, I'm just going to show it to you here and sort of see if you can get some idea what's going on. Now we'll have to speed it up quite a bit. So what's actually happening is this is a well-known pattern that's called a galaxy. It's a period 8 oscillator. And it's going very slowly right now. If you look at the generations, we're sort of going 10,000 generations a second or so. And that's because if you zoom in on this, there's a lot of machinery that's going on there. All of those squares are actually made by these guns all around the edge that are shooting spaceships at each other. But what's interesting about them is that they've got a way to turn them on and off by firing something around. So, whoops, that's the wrong word. Yeah, so let's just. So at some point, see these things going around there? Those things are actually keeping track of how many of the cells surrounding the one cell are active. So what this thing is actually doing is it's computing the game of life, like that. And of course, once you can do that, the next step is, well, why don't we just build a general computing machine? So someone decided to build a Turing machine. So early on, it had been demonstrated that the game of life was universal, which meant that it could emulate a Turing machine, but actually being able to engineer one was another matter. This one is a fairly simple one that has it's got 3 states and it has 3 possible symbols. This is the tape here. Rather than actually being a tape, it's implemented as 2 stacks. So you can store data on each of these cells, and you can also move the data sort of one step over. So you can sort of pop stuff off the stack and push stuff onto the stack, and similarly over there. So rather than the tape moving, the read head and the tape stays stationary, but it just sort of pops things on and off the stack. And then these cells here keep track of the state of the machine, tell it what to do when each symbol actually gets made. It's kind of hard to really see things happen, and you occasionally see a few gliders moving around that represent bits in the program moving. And of course, the very last thing, this was made in 2000. Until in 2011, the same guy made this. The other Turing machine wasn't a universal Turing machine. This one is. So, and not only is this universal, but he wanted to make the stack infinite. So these long diagonal constructors here are actually sort of like those breeders, except rather than making a line of those guns, they actually make more of the stack, and they build it faster than the machine can use it. So this one is, like, even on my new laptop, it kind of taxes it a lot to actually run this one at any reasonable speed. But, and of course this one, you decide to really go to town. You don't really need, you can definitely do a universal Turing machine without that many states, but I think this number just happened to be sort of convenient for what he was trying to do there. It's jerky, but you can see it sort of building the stack there. If we zoom out, see these gliders going in there, that's actually the data being fed into the stack. So those are all push instructions. The computation hasn't even actually started yet. Anyway, that's probably about all the time I have, so we'll just say any questions. Yes?
What are these models and structures applied to, or what are they used to actually model in real life or in engineering or whatever, if they are?
Yeah, cellular automata, like, they were sort of invented to kind of try to model, like, sort of cell growth and stuff like that. But they've sort of thought of other applications that they've thought of are sort of for trying to coordinate like groups of robots and that sort of thing, like having just sort of a simple, having a lot of very simple machines. By communicating with each other, they can sort of demonstrate complex behavior. In some ways, it's like a very simplified model of a neural network as well. Basically, it's a big parallel processor. Each one can be sort of thought of as a neuron, but whereas in the brain and in other neural networks, you kind of tune exactly how parameters are weighted. Or in this case, the connections are very regular and the parameters are sort of all the same. But mostly it's been a way to just study how complex systems can, how very simple systems can evolve into complex behavior without there really needing to be a initial source of complexity. Yeah?
Thank you. Thoroughly interesting. Can you talk a little bit more about Golly?
Yes, actually, I should have said that. So all of the information here, if you want to learn more about Game of Life and that, you can go to www.conwaylife.com. There's a wiki there, and there's also a link to download Golly from SourceForge. So it's just a tar.js. I think you can run it in Windows as well. But I've always just sort of locally installed it in Linux. I think there's like one package that I needed to install to get it running. But yeah, it's been around for a long time. It's pretty easy to use as well. So yeah, if you definitely want to play around with these, and you can play around with a lot of other simulators as well as like a lot of other rules and things. And most of these patterns here, I kind of customized them for this talk, but a lot of them are preloaded into the program as text files. So you can have a look at all of these patterns right away.
Conway is the same with the author of the Conway law?
The Conway
Law
law?
in software engineering that says that
might be.
okay.
He did a lot of different things, and I came to software sort of late. Haven't actually ever been to no idea what that is.
Different Conway.
It is different Conway? Not John Conway?
No.
So what's the philosophy, for example, with that prime number generator? Yeah,
Yeah.
is any analogous? Can you do an analogy with another computation?
Oh yeah, they've. I think there's definitely someone who's. Well, actually, I don't know if someone's done the digits of pi. I think they did the digits of like. Pi is a little trickier to do because the formula is complicated. But for doing something like a square root, I believe there have been a number of patterns that have been done to just do the digits of that binary or whatever. I'm sure someone's attempted pi. I just don't know for sure whether it's actually been done. But I mean, you can always calculate it using the universal Turing machine, but that would take a long, long time.
My question is, the philosophy of the initial pattern. What gives that initial pattern the power to generate, for example, prime instead of square?
Yeah, no, it is a similar thing. Like if you look at the prime numbers, they seem somewhat randomly distributed, but there's no actual initial random information. It's just the way numbers work. Similarly, pi, it looks like the digits are random, but there's not actually randomness there. It's just the way it works. So, in fact, Stephen Wolfram wrote a lot about cellular automata, particularly one-dimensional ones, and you can make a one-dimensional cellular automaton that basically computes the primes, and so it's like that's not really a special one. A lot of these different cellular automata have that property where you give it no basic starting information, but it still seems to generate randomish looking information just as a result.